Oh, I want to play Fortnite so bad. But first, IChO 50, problem 7, Cidofovir. So, IChO 50 2018. So, let's solve problem 7. Problem what? So, problem 7. Alright. Okay. Let's see. So, 7.1 asks us to draw from A to D, including stereochemistry. Only one molecule of A produces 2 molecules of B. Okay. So, let's see. So right here is L-mannitol treated with acetone and zinc chloride to give you product A. And so the product would be an acetal formation, right? 1, 2, 3, 4, 5, 6. So it would be an acetal formation. So they treat it with acetone. So it's going to be that's going to be a dash like so. And what next? And right here also. And then you will have the wedged hydroxyl groups coming out of the plane. Great. And we can use the DBE to see if we're correct or not. So it's going to be 12 times 2, that's 24. 24 plus 2, that's 26. Minus 22, that's 4, right? Divided by 2, that's 2. So from the DBE equals to 2, we can say that there must be only 2 acetones that will be used to form an acetal. So because there's only 2 DBE, and that fits 1, 2. And from the clue right here, it says only one molecule of A produces 2 molecules of B. And this is A, and we treat it with sodium periodate. That's going to cleave the diol and form an aldehyde. So it fits to the clue that only one of these form 2 of B. So it really fits, because cleaving in the middle, that's just going to give you 2 of B's of B, right? So yeah, that fits the clue. 2 of the DBEs and 2 molecules of these. Sodium periodate will cleave that, yes. And then next we treat it with sodium borohydride. That's going to reduce the aldehyde into the alcohol. What's next? Then we treat it with a strong base and benzobromide. So that's just going to be an SN2, right? Deprotonation of the alcohol, and then a benzo group will be applied, and aqueous hydrochloric acid will okay, yeah, good. And then aqueous hydrochloric acid will take off this acetal, and you will be left with 2 right here, which is denoted right here. Great, let's continue. Draw the structures of all alternative stereoisomers of compound 3, which if used in the same reaction sequence give exactly exclusively product 2. The structures of all alternative stereoisomers of compound 3, then what is 3? This one, L-mannitol. That will give 2. So what really matters in transformation of 3 to 2 is this stereocenter, right? These are the only stereocenters that matter, and we have to keep it locked like this. But for these stereocenters that bears the OH that are wedged, as you can see, it doesn't matter, because after treatment with sodium periodate, it's going to cleave us and give us a non-stereo center anymore. It's not going to be a stereo center anymore, so it doesn't really matter. So what we can do is, I'm just going to copy the structure. So what we can do is we can have 4 stereoisomers that we can use, right? So the first one is already given to us because, well, it's in the problem. So the first stereoisomer is this one, right? But it says all alternatives. So well, we have to change things up a little bit, because this stereoisomer has already been given. So this is the first one. And the second one will be all dash. And all dash. And actually, and a wedge right here. Yeah, but the thing is, this and this is exactly the same. So these two are the same compounds. Because if you look carefully, that's 1, 2, 3, 4, 5, 6. And if you come from down to up for the right compound, 1, 2, 3, as you can see, it has the same what you call this? The same absolute configuration. So okay, there's only 2 stereoisomers, alternative ones, because this one and the one that I drew are the same. Okay, I didn't realize that when I was thinking in my mind, but when I draw it out, okay, yeah, they're the same. Then diol 2 is further modified to provide compound I. The synthesis of phosphonate 4 is used to convert F to G, will be discussed later. And I really love the hosts for IChO 2018, IChO 50, because they give us a small scheme right here, which we can use, because if they don't give us this, we have to flip back and forth. What a hassle, really. So yeah, they're really generous for this. So thank you very much, Czech Republic. So for E, we treated with MMT chloride, and that 3, that's going to be a kind of a protection, similar to that, similar to protection. And this will be the OH, this will be the OMMT, right? OMMT. Great, F. That's sodium hydride. That's going to be deprotonation of this. And they didn't put any charges on F, so we also need to draw the counter ion. Not really draw, but write the counter ion, which is sodium. Great. That's deprotonation. Then F treated with this phosphonate ester, which also bears a leaving group. That's going to give us the phosphonate ester right here, POET2. Nice. That's really great. G, that's G, right? Okay. Then next we treat it with hydrochloric acid. So we treat it with hydrochloric acid. That's going to remove the MMT group. Hydrochloric acid. And, oh sorry, not hydrochloric acid, acetic acid. Then we treat it with, that looks like a mesyl chloride. So let's put a mesyl group on the OH. You know, that's mesyl chloride. They also gave us the molecular formula on the answer sheet. That's really, really generous of the hosts. I love Czech Republic hosts. I mean, they're the first host to host it. I mean, they're the first country to host the IChO. So, you know, they know how it's done. All right, phosphonate 4 can be prepared according to the following scheme. Draw compounds J to L. So we need to work backwards here, because we need to know J to know K, but since we don't know both of them, we need to work backwards because we know 4. So 4 treated with tosyl chloride retro, that's just going to be an tosylation of an alcohol, right? So we can just safely say that this should be our product before treating it with tosyl chloride. Great. Then the next step, the step before that, we treat with sodium ethoxide and a proton. So I think I have a feeling here that I have a feeling that this part right here is eerily similar to this. So I'm gonna say that K is the acetate version of L. It's a transesterification if you will. So from the so before this acetate group, I mean, this exists like this, right? And then after we treat it with sodium ethoxide, you'll get the ethyl acetate, right? You will get that out, and then you will get L as a product. So yeah, I think that's how you do it. So we're okay. Then can know J. So if we want to transform this to this by adding J, then J must be this compound. So it can substitute on the bromine and then condense into a PO double bond, like so. Great. Very great. Oh, there's a... Oh no, that is for the next question. Direction from I from question 0.3. Oh, here we go. With cystosine. Okay, whatever. I'm way too lazy to read that. All right, let's see. And that's okay. The last two questions. Okay, so we have 5 and P. Draw the structures of two isomers M and N of compound O, including stereochemistry, and the structure of the aromatic tautomer P of cystosine. The transformation of M to O is a removal of a protecting group. So from 5 to P, that's just the tautomer. And where do we draw P? Oh, here you go. So that's just going to change this amide with a lot of speech marks into a pyridine. So that's basically a pyridine, but a fancy pyridine, like so. Hydroxyl group, and the amine sticking out like so, right? Looks like this. Great. Okay, good. Now then we treat it with compound I, which is this compound, and then we treat it with a base, cesium carbonate, and we can actually use some clue to see that, oh, what is this? That's similar to our product M and N, but M is formed in 75%, and M is then being used to O, so that tells me that M is this isomer. So M is just going to be which one? I need some reminders. I have a really short-term memory. Maybe it's because I don't eat enough fish. But who knows? Top 10 reasons. I'm trying to draw this pyridine ring as beautiful as I can. Is this beautiful? I hope this is beautiful. Oh, it looks acceptable. I'm a very serious person when it comes to drawing pyridine rings and other rings. I'm just speaking gibberish now. I need a reminder of I. Okay, so that's going to substitute on the O-methyl group. That's the leaving group. OMS, that's a good leaving group. 1, 2, 3. Yeah, that's 3 carbons. OBN right here. This is the phosphonate. OET2. Okay, great. That's M. N is just going to be the treatment of the other tautomer. It's just going to be this tautomer treated with same base and compound I. So it's just going to be using the oxygen instead of the nitrogen to connect to the compound I. I think I should draw this as a pyridone, actually. It's not really a pyridone because you have 2 nitrogens in the ring, but who cares? so it's just going to, it's going to be so hard to draw. Okay, let me draw the other way around. Nitrogens right here, and the ring right here. This will be the NH2. There you go. Great, that's N. All right. Treatment of M with cyclohexyl 1,4. Cyclohexyl 1,4-diene, cyclohexan 1,4-diene, whatever. With palladium on carbon, and it tells us that this is a removal of protecting group. And what's clever here is that normally when you remove the protecting group, in this case is the benzyl group, right? When you remove a benzyl group, you would use what? H2PD on C, right? But for this one, they didn't use a hydrogen purely. They didn't use hydrogen in its H2 form. They use hydrogen in a form of here. You see? So the hydrogen will be consumed from this cyclohexadiene and will remove the benzyl group, right? So your O, okay, first will be a deprotection, right? Oh, sorry, we need to copy from M because M is being used to get the final product. So it's going to be OH. Then the byproduct Q and R. Q is from cyclohexadiene, so it is going to be benzene because it's going to use the two hydrogens on the cyclohexadiene to deattach to remove the protecting group. And for the protecting group, the benzyl group is just going to be toluene. Great. And yeah, that's it for IChO 50, problem 7. Cidofovir. Very good problem. A really fun problem to solve before getting on to the harder ones. And thank you for watching.